Hello everyone, and welcome to your video tutorial to help you with your motion detector lab, where you are going to approximate the value of g, or basically the value of acceleration due to gravity during free fall. Okay. And what we're going to do is we are going to model this experiment after Galileo's experiment. Around Galileo's time, it was unclear whether falling objects fell at a uniform rate of acceleration. It was kind of the mindset that the heavier the object, the faster it would fall. And the reason for this being, the argument that everyone made was the feather in the bronze ball, in the sense, if you drop a feather and a bronze ball at the same, in the same room, not in a vacuum, well, of course they're not going to fall at the same rate because you have air resistance. But Galileo devised an experiment where he had a long piece of wood, and he says it's 12 cubits long, which was their unit of measure, and it was polished very smooth in order to reduce the effect of friction. So that would be definitely a source of error there. And he also rolled a very smooth bronze ball. Again, key to being smooth is to reduce the amount of friction. And so what he did is he angled this board, so he probably propped it up with something. So he's got some angle here, which we'll call theta. And he rolls the ball down, and he timed it, and their unit of time was it says in the papers, a pulse beat. Now, it's unclear if that is a human heart rate or if that is a metronome, but they have a different unit of time than we do. But in the experiment, it says that they do a roll at the same angle over and over again until they get a time that is within half a pulse beat of, or excuse me, 1/10 of a pulse beat from the other. So that makes me think it's not a human heart rate, but anyway. And so what they do is they get this length here, which we'll call L. And that's the length of the ramp. Okay, and then they get a time, which I'll call T1. I'll call this L1 and T1. And that T1 is for the time necessary to cover the entire distance of the ramp, so the whole ramp. Okay, and so then what they did is they repeated the experiment, but they rolled the ball a quarter of a length. So they did L1 over 4. Okay? Now, if the ball was moving at a constant velocity, then its acceleration would be 0, and so the time you would expect would be T1 over 4. But instead of it being a quarter of the time, it took half the time. So it covered a quarter of the distance in half the time. Okay? And they repeated the experiment for 1/2, for 2/3, for 3/4, and at each of those times, the spaces traversed, in other words, the space is covered, so whatever L was, were the squares of the times. Okay? So, in other words, if I squared, let's say I did T1 over 4. In other words, I took a quarter of the time. Well, if I square that, that would mean I covered 1/16 of the length. Okay? So, when we think about the units of acceleration that we know and love, meters per second squared, that's where the squared comes from. Okay? And so Galileo rationed out that it must be d over t squared for this value of acceleration. And you're going to go about this a couple different ways. You're going to model your first method is to model Galileo and come up with this ratio between length and time. But your second method, what you're going to do is you're going to gradually increase the angle theta. Okay, in other words, how the ball is falling. So you're going to gradually increase your ramp. And what you're going to do is you're going to get a limit of this ratio. Okay, and the limit is going to be as theta approaches 90 degrees. Okay. Now, I don't want you dropping your carts straight towards the motion detector because that would mean that we'd need new motion detectors. But what you are going to do is, this is going to be your setup. You've got your motion detector, like so. There's your ramp. You are going to measure your angle theta. Easy way to do that is to measure the length of your ramp and then measure the height that you raise your ramp to, and then using trigonometry get that angle. And then the motion detector is going to give you a position versus time graph. So you're going to start your cart over here. It's going to give you a position versus time graph. And it is also going to give you a velocity versus time graph. Okay. Now, since this acceleration is constant, what I want you to do is use your velocity time graph to get the value of acceleration. Okay? So what you're going to measure is you're going to measure your angle theta, which is going to be like your independent variable, and then your value of acceleration. Okay? And the goal of this is to come up with a plot that will give you a straight line. Okay? Now, your position versus time graph, I'm going to give you a second, pause the video or whatever, and if I'm dropping the cart like this and it's going towards the motion detector, my V initial is 0, draw what your position versus time graph looks like. So go ahead and pause the video. Okay, hopefully you've got a position versus time graph drawn. And I'm going to draw it for you real quick. So we know that we are starting away from the detector. So I'm going to start here. And I know that I'm moving to the left. In other words, I'm moving back towards the detector. Now, since I'm moving to the left, I'm starting from rest also. So that means my slope should initially be 0, but then the cart should speed up. So you should get a graph that looks like that. Now, for your velocity versus time graph, I know that I start at 0, and I am moving in the negative direction. So that means that my velocity versus time graph looks like that. The slope of this line should give you A. Okay? So tomorrow I'm going to show you how to use the motion detector to get the slope of that line. Okay? So again, the data that you are to collect, your angle theta, and the value of acceleration that you get from this slope. Okay? Now, the goal of this is to get a linear relationship between theta and A. Okay? And so, a couple ways you can go about that. You can graph A and theta, just A versus theta. You could graph A versus sine theta, A versus cosine theta. There's all kinds of options that you can graph, but you want to arrive at a linear relationship. Okay? Now when you think about this, if theta is 0, that means the ramp is flat. What value of A should you have? 0. As you increase theta, think about what your graph is going to look like. This graph should give you the value of A, the limit as theta approaches 90. That's going to give you the value for G. Okay? So you want this graph, and then try and find a graph that will give you a linear relationship.